let's implement this method together. I guess there are basically two approaches, and some of you came up with similar approaches. The first approach is we are going to just find the mean value first using the find mean method we implemented. And then we are going to find the mean index using the Python default method, meanval, like this. And then we're going to pop the value at mean index. Then we're going to return the mean value. So this is one solution. And the thing is, it takes two for loops, one for loop and the second for loop. So it is going to be something like O2n. And another way we can improve this solution, although it's going to be same O log n, what we are going to do is first define two values. The index I and x is going to be the value of the first element. And what we are going to do is iterate through all the values inside this data, and we find the mean value. If this value j is smaller than x, then we're going to replace the minimum value x with this new value at position j, and we're going to change j with I. And after this one for loop, we're going to pop the value at I, and we're going to return the minimum value x like this. So it takes just one for loop, because this takes O1, because we know, if we know the position, we can use rem, so it does not take more than O1 operation. So both are okay. And some students came up with one-line solution, like this. This is also okay. So any questions regarding this method? Okay, let's move on. We are going to use from now, so we use simple Python list to implement a priority queue. And what we are going to do from now on is we're going to use sorted Python list to make this simple Python list a little better. So that's what we're going to do from now on. So basically the constructor is the same. We're going to just copy this code. And when we are inserting a new item, we are going to do somewhat different things. So what we are going to do is we are going to attach the smallest value at the end of the list. So what we are going to do is smallest value, smallest item to the end of the list. So this is what we are going to do. So what we are going to do is we search through the items inside this data list. And if this value is smaller than this value at position I, we're going to increment I one by one. So we find the right place for this new item X, and we're going to insert this new item at position I. So that's what we're going to do. In this way, when we're doing inserting operation, the items inside this internal list are sorted. And once we do this, find min operation becomes very, very efficient because we just need to return the item at the end. So it's going to be 01. However, insert takes more time. And delete min becomes also very efficient because we just need to pop the last element. So in this way, by sacrificing the insert operation, you can make find min and find and delete min operations very efficient. So this is one way of making priority queue somewhat more efficient. However, what we want to do is make all these operations O log n. So sometimes it takes On, and the average time complexity could become On rather than O log n or O1. So to make all the operations O log n, we're going to use binary heap. Another thing is if insert operation is very rare, and if we use find min and delete min operations much more than this insert operation, then we can follow this implementation. However, if we use all these three operations quite a lot, then we better use binary heap because all the operations take O log n. And to implement binary tree, I told you that it is a special type of binary trees. And there are two ways to implement binary trees. The first one was linked list using nodes. And another way is using arrays. However, we are going to use arrays in this case because the binary tree we are using is complete. What I mean by this is, let's say we have tree at this position like this, and we have children like this, second position, and third position like this. So this is complete. However, if we can add new items like this, then we better use linked list because the binary tree can have arbitrary shape. However, we are not going to deal with these types of arbitrary shapes of binary trees, but rather we are using complete binary trees. So we are going to use arrays because the implementation becomes very, very simple. So what I mean by this is, in the case of binary trees, complete binary trees, there cannot be any items like this. However, we first need to fill the third level before we can add new items at the fourth level. So when this happens, one cool thing is, I'll show you what this is. So let's have a look at the indices of these nodes. So when the trees are complete, if if the parent, the index of the parent is P, then the left child will have the index 2 times P. And the right child will have the index of 2 times P plus 1. So as you can see here, if we want to know the position of each child, the left child, then we just need to multiply 2 to this position. Then it's going to be the index of the left child. And if you add 1, then it's going to be the right child. And in this case, you can do the same thing. Like multiply 2 to 3, then it's going to be the index of the left child. And this is this makes the implementation of a binary tree very, very efficient and easy. And we can find parent from children. So let's say if a child's index is Q, then its parent will have the index of Q divided by integer 2. So if you just divide 7 by 2 using integer division, then it's going to be 3, because we are just deserting the remainder, then it's going to be 3. So we can find the indices of children and the parent very easily if the tree is complete. So we are going to use arrays rather than linked lists to implement binary trees. So this is what we are going to do. So let's implement priority queue using arrays. We are going to define the default capacity of binary tree as 100. Then what we are going to do is first we need to define the constructor. We're going to place none inside this list times priority queue default capacity. And we are going to keep track of the size, because at first we do not have any items, so the size is 0. And now we can support the land method. We're just going to return self.size. That's what we can do. And we're going to implement find mean operation that is going to be just return the element at the root. By the way, in the case of array-based binary trees, we are not using the index 0, because if you just start to place elements at the position 1, then implementation becomes easier. So we are not going to use the index 0. However, we are going to use from index 1. So the minimum value is going to be at 1, position 1. And we're going to implement the insert method. As I told you in the class slides, what we are going to do is because we need to maintain the heap order property, we are going to place a new element at the last place here and bubble up until it finds the right place. So that's what we are going to do. How are we going to do that? We first need to check whether we can add new element. So if you add one more element, and if it becomes the land length of the list, that means we cannot add new items. In that case, we're going to double the size of our list. So this is what we discussed before midterm, like this. And what we are going to do is increment the size by 1. And we're going to find the whole. And this place is going to be a whole. So before we insert any new items, this one is whole. And if this value is smaller than the parent, then this whole is filled by its parent. So 4 goes here, and this place becomes whole. So that is the concept. So rather than placing 2 actually at this position, we are not putting 2 here unless it is the right place for 2 to come here. So we are going to keep this place as a whole, and we're going to fill this hole with the correct value. So this position is first whole, and what we are going to do is bubble up. So while this x value is smaller than its parent, because I told you that we can just find the index of parent by dividing this index using 2. The parent's index is going to be whole divided by 2. So this is going to be parent's index. And if this value is larger than x, then x needs to go up. So we're going to place the value of its parent to this whole, like this. And we're going to divide the whole, and we are inspecting the next value. So after we run through this while loop, whole is going to be the correct place for this new item x. So this is how we implement insert method. So now you might be able to understand why we are using arrays rather than linked list to implement binary heap. And if you use binary heaps, this bubbling up process is going to be very, very complicated. However, because we are using arrays, this operation becomes very easy to implement. Okay, the next method we are going to implement is delete mean. So in the case of delete mean, what we did was first remove this value and place the rightmost value at the last level to this position. And we're going to bubble down. But before we do that, we need to find the small value among its children. So that's what we are going to do. So the mean item is returned by this find mean method. And we're going to place the last element to its root, like this. And we're going to decrease the size by 1. And we're going to bubble down starting from the position 1. And we're going to return the mean item. And we're going to implement bubble down. And bubble down, for bubble down, this parameter means we're going to bubble down the item at position I. Okay. And when you're implementing this bubble down method, you could implement smaller child. So you're going to receive two values, the index of the node you want to inspect and the value of the node. And this check inspects whether one of its child is smaller than the element's value. So this is the first thing it inspects and returns the index of the smaller child, or 0 if no child is smaller. So you can implement these two methods. So this is our TPP exercises.